All right, in this video, we're going to take a look at a related rate problem dealing with distance. So let's jump right into it. In this problem, we have the Goodyear blimp flying due east at 16 miles per hour at a constant altitude of 2 miles. If the blimp flies over a stadium at noon, then how fast is the distance between the blimp and the stadium changing at 12:15 p.m.? Okay, so in our related rates video that I posted before, I said there's 3 key steps. And the first key step on a related rate problem is to identify the rates of change. And again, these are identifiable by the units a lot of the times. So for example, meters per second is a rate of change. And in this problem, we don't have meters per second, but we have miles per hour. So I see 16 miles per hour. I know that that's a rate of change that I'm going to have to write down in a little bit. Secondly, a related rate problem, the question itself is always a rate of change. So in this one, how fast is the distance between the blimp and the stadium changing? Well, that's a rate of change, a dx dt or something like that. Now this problem doesn't talk about volumes or widths or anything like that, so typically the best way to assign a variable on a problem like this is to draw a little picture. So I'm going to draw a picture. You don't have to be a great artist, so we're just going to draw a little box for my stadium, and my blimp flies over the stadium at noon, and it's flying at 16 miles per hour to the east. Okay, and really what I want is the picture at the time that it's asking the question. So it asks the question at 12:15 p.m. So I really want to know that the blimp is over here, a little bit to the east at 12:15 p.m. And that's where I want to kind of draw my picture of what's going on. Okay, so it's asking about the distance between the blimp and the stadium, and I'm just going to draw a line connecting the blimp and the stadium together. So it's asking about that distance there. Okay, and I can assign a variable right here to the picture. Now typically I don't like to use d's for distance on these types of problems because you'll be taking derivatives, so you'll have things like dd, dt, and it just looks weird and sounds weird when you say it. So I typically assign a z for a distance in this problem like this. Okay, now what else do we have? Well, we have the vertical height, the altitude, which is always the same. And remember, when you're doing a problem in related rates and something is not changing, don't assign a variable to it. So I just want to put in 2 miles there. Okay, and then the last side is, well, just how far east this blimp is going, and I'll call that x. Okay, so going back into the problem, it says that the blimp is flying due east at 16 miles per hour. Okay, so that means that x is changing, dx dt is changing at 16 miles per hour. Okay, the other rate of change that it's asking about is how fast is the distance between the blimp and the stadium changing at 12:15. So it's asking us how fast dz dt. Remember, all your derivatives are with respect to time in related rate problems. All right, so these are the only 2 variables that are changing in the problem that are being asked about. So what I want to do is find a formula that relates these 2 variables together. Okay, now when you're talking about distance, there are typically 2 ways to do it. You can either use the distance formula if you're on the xy plane, which we're not, or you can typically use Pythagorean's formula. And in this case, there is a little right triangle formed by the blimp at noon, okay, the blimp at 12:15, and the stadium. So we can use Pythagorean's formula to say that z squared is equal to x squared plus 2 squared. Or simplifying, z squared is equal to x squared plus 4. Okay, so now I have a formula that relates together the variables that are changing in the problem. And now the third key step is just to take the derivative with respect to time. Now, remember, when you're taking this derivative with respect to time, you're going to have to use the chain rule. So you'll use your normal power rules. For example, the derivative z squared is 2z, but whenever you take the derivative of a variable, you're going to tack on dz or dx or dy dt. Okay. On the other side, the derivative x squared is 2x, and again, we need to tack on dx dt. Okay. finally, the derivative of 4 is just 0, which you don't have to write, but I will write there plus 0 just so you see where it went. Okay, so now it's asking us what is dz dt. So in order to solve that, I just need to figure out everything else. Well, it already told me what dx dt is. Okay, 2 is just a number in this expression, so I need to figure out what z and x are. So we'll have to do a little bit of side work on this problem. Okay, so if we look back at the problem, at 12 p.m., the blimp was right over the stadium, and the question is asking us about 12:15. Okay, so how far would x be if you flew from 12 to 12:15 at 16 miles per hour? Well, we can use the distance formula. Distance is equal to velocity times time. We know that the velocity is 16 miles per hour, and the time is 15 minutes, or 15/60ths, or 1/4 of an hour. So we're going to have 16 times 1/4, or 4. Okay, so that's going to give us what x is. Okay, so now we need to figure out what z is. Well, remember that z and x are related together by Pythagorean's formula in this problem. So z squared is equal to x squared, which is 4, plus 4. So 4 squared plus 4. So z squared is equal to 20, or z is equal to the square root of 20. Okay. All right, so now we have all the pieces we need to figure out what dz dt is. Okay, so going back to our derivative that we took, we have 2z, so 2 times the square root of 20, times dz dt, okay, is equal to 2x. X we calculated to be 4, times dx dt. Okay, and again, dx dt is 2 times 4, and dx dt, we already wrote that down to be 16. Okay, so overall we can solve this pretty easily for dz dt just by dividing. So we'll have dz dt is equal to 2 times 4 times 16 all over 2 times the square root of 20. Okay, so now it's just calculator time. We throw this all into our calculator, and we'll get approximately 14.3 miles per hour are the units in distance changing in this problem. Okay, as always, thank you for watching. If you liked the video, make sure to like and subscribe to my channel.